Sorry for the abrupt cut there. I was having so much fun. I was so excited I just didn't even notice the timer on the camera. So we'll try to pay better attention. So now I feel a little disjointed. So I'm just going to jump in here and use IQ as an example. So what do we know about IQ? IQ is standardized so that the mean of a sample is shifted until it equals 100. And we know that each standard deviation represents 15 points. So when you're looking at IQ as a test, what do we say? Mean of 100, standard deviation of 15. It allows us to make our calculations in this regard. So if someone scores 100 on an IQ test, we consider that average. There you go, 100, 115, two standard deviations, then is 130. And this is the threshold for gifted. Down, coming this way, 85, then 70. This is kind of the threshold for differently abled. No. This is going to allow us to, like I said, to compute percentages as well, and it allows us in our predictive abilities. If we need to hire people over 130, then we can actually calculate what percentage of people in a given randomly drawn sample will have that. So if we need 15 people, we can work backwards and say, wow, 15% of the people, it's only 2% of the population. We do the math and then we understand how many people, how many candidates we need to attract. So z-scores tell us how many standard deviations from a score is away from the sample mean. And a z-score of 2.5 means that someone is 2.5 standard deviations above the mean. That's why we calculate to z-scores, is because it allows us to then kind of use a more comparable number to other measures, right? A z-score of minus 0.75 then would pull us the other way, means someone is 3/4 of a standard deviation below the mean. So in that case, if we were 3/4 of a standard deviation, it would put us right about there. Or an IQ of, let's say, 80, 89 perhaps, if we do the math. So that's just rough math in the head. So what do we need to calculate the z-score? We need a large enough sample, and that's something we should be sensitive to when we're looking at the, like for example in a find and measure assignment, we want to know what was the sample size in which this was calculated. We also want, for our purposes, a measure that has a broad enough range so it actually differentiates candidate. It does us no good to give someone, our candidates, a measure that's scored from 0 to 15, and everyone scores a 15, then it's not a useful measure because it didn't differentiate the candidates, right? So we need the mean of all candidates on the measure, right? And then the standard deviation of that measured sample. And from that, then we can calculate the z-score. And let's talk about calculating a z-score. How do we do it? And this is part of your assignment, right? This is number 11, so you'll see this spelled out, right? You got two data tables to work with there. Divide the result by the standard deviation, right? So we subtract the mean from the score. We divide the result by the standard deviation. So, for example, if mean IQ is 100, which we've already said, and standard deviation is a 15, that's our given, right? We have an individual who scored 130 and we say, hey, good job, but what does it mean? Well, we take 130, their score, we divide it by the sample mean, and we get then 30. 30 divided by the standard deviation, the difference divided by the standard deviation equals 2. 2 is the z-score. So the individual z-score on the IQ test is therefore 2, which means they scored 2 standard deviations above the mean. Let's look back at that chart, and what do we have? Okay, they scored 130, 100, 130, minus 100 is 30, 30 divided by the standard deviation, 15 is 2, and look, 2 standard deviations above the mean. So I hope that kind of clarifies the relationship between all those numbers. It's not super mysterious by any means, right? So, calculating the z-score we've covered. What do z-scores allow us to do? In effect, they allow us to compare hot potatoes to chilled bananas, if you will. And I'm going to attribute that to Alex Fenarn, a student I had in a couple classes back in 2007. I loved Alex. Alex, a brilliant young man, and very thoughtful, always came to class prepared, and always would pull out, almost every class session would pull out a question I couldn't answer, which was kind of cool, because I don't have the answers to all questions. And I think it's fun. I think it's a good exercise to stand up there and say, I don't know, what do you think? So that was, and I remember in psychology creativity he was especially good at that. So, and I still talk to Alex on occasion. So for example, one might have the top score on a measure of self-monitoring and be toward the bottom score of self-handicapping. Another, the two measures that we looked at in the previous lecture. The idea is, though, we have to be able to combine these scores in some meaningful manner, right? And one score might be generated on the scale, like I said, from 0 to 100. Another might have a score that's only from 1 to 5, if let's say it's a banded item that we used as an example earlier in this. So z-scores allow us then to make those scores comparable relative to each other. Because we're no longer talking about raw points, we're talking about the distance from the mean in terms of standard deviations. That is the z-score. So the beauty of this is it allows us then to, like Alex said, compare hot potatoes to chilled bananas, if you will. So they allow us to compare level of performance on one construct to another, and ultimately allow us to create a final score, a final ranking score that will determine our selection of candidates. So, mentioned earlier, in determining sample size or the number of applicants we might need if we have this data available to us and we want to hire at a certain level. Here's the deal. What do we know about standard deviation and proportion? Well, the way this is constructed is the mean, right, stands in the center. 68% of a given sample, when we have a normal distribution, will be one standard deviation below or above the mean. So this represents two standard deviations around the mean. 68% of our sample will fall in that. So this ability to use this space under the curve to calculate proportions allows us to predict how many applicants we might need to achieve a certain level of hiring, if we know the data in advance, right? So 68.26% of the area. This, if we were using IQ, then what do we know? That we know that 68% of the population, let's say in the United States, has an IQ of somewhere between 85 and 115. Fully 95% of the people in the United States will have an IQ between 70 and 130. And then finally, if we look at the tails, and that's the small end of the distribution, let's say what's the number of people in the population who have an IQ above 130. And we see that that is roughly about 2%, give or take, of the population. And then those who are mentally challenged would be roughly 2% of the population as well. So this, in fact, allows us to better understand how a trait or how any performance measure is distributed within the sample. So the standard normal distribution then, normal distributions have similar shapes but can differ on their mean and their dispersion. The idea here is we might take an existing distribution, do some statistical magic to convert it to a standard normal. The standard normal distribution is a normal distribution that has these characteristics. It will have a mean of 0 and it will have a standard deviation of 1. Right? This allows us to calculate the proportion of our sample that's above or below a z-score, and this can represent cut points. And the idea of cut points, again, is kind of associated to banding, that we may, in fact, want to view our sample in terms of its discrete position on a distribution. So z-score and proportion then, 30% of our scores lie between the mean and z, and this would be 1%, is 34%. So maybe a little less useful, but it still tells us about our potential sample within a population, right? And if a distribution is normally distributed, then one standard deviation above to all the way down below is 84% of our sample, and we can flip it around to the other way. But take-home points from this, right? What you really need to consider, what I want you guys to consider, is moving through the z-score calculations, because ultimately what we're looking at is bringing a candidate in, maybe subjecting them to a personality or trait test, right? That might be one item. And then we may have them do a standardized interview, which is scored with a very specific rubric, and the rubric might score their interview performance from 1 to 5. Then we might have some kind of work or behavioral type test that we score in terms of a score from 0 to 20, right? And then we might have another test that is scored on 0 to 100, but it's banded in 20 band increments to represent bands 1 through 5. Somehow we have to be able to add those strange different numbers together to determine the candidate's ultimate ranking. So that's the statistical magic that we learn and we employ to get this done. And let's kind of look at the bigger picture now coming into 3.24, which will be in fact our final lecture for today, and will tie to the activity number 12.